Alright guys, so this video is about to learn how to use the MATLAB part. So basically this is the main file where basically you just need to basically this is the function define, function f in function of t and y, sine 2t minus tangent t times y. Initial condition is over here, so we can maybe specify that. Say this is the initial condition, and this is the initial time, this will be the final time, this is the number of steps. So if you want, again, we can set that. So initial time, this will be the final time, and this is basically the number of points. All right, so this is the interval, integration time. This is the time from t initial times step to t final, and now you solve using ODE1. So ODE1, what is ODE1? ODE1 is the Euler method. All right, so let's see. If I go here to camera app, hopefully we're gonna get there. So this is the camera app. All right, so here we go. Our Euler method was this function over here. So now you see it's just f, k1 is f of yn, tn times delta t, yn plus k1. Can close that. So what is ODE1? Basically, you see that's what it is for each time step, from t initial times step dt to t final minus 1. This is just to keep copying the file at I plus 1. K1 is as we define it over here, and the function y becomes y, or y plus 1 becomes y plus k1. Okay, and this is just to save the data. All right. So similarly, ODE2 is the modify Euler's method, which basically is just define, you do one middle step over here before you calculate y. So that was becoming, again, you see over here is k1, k2, and then plus 1/2 k1, k2. Same, identical as before. All right, so here we can go to the camera, and if we look at the second function, what is the modify Euler's method? K1, k2, yn plus 1 equal to yn plus 1/2 of k1 plus k2. All right. So similarly, so ODE1 basically means the first order approximation. All right. And ODE2 will mean second order approximation. So this one is first order approximation, second order approximation. The second order approximation equation we had was the Heun's method. All right, and this time what did we have? K1 equal to f ty dt, K2 equal f at 2/3 of dt. You calculate at 2/3 of K1, and then it's 1/4 of K1 plus 3 times K2. Remember that this always needs to be equal to 1 with the coefficients. All right. So again, I have it behind here. Maybe I can just click here. Heun's method, you have it over here. All right. And then Runge-Kutta, you see, is again about the same thing, but this time is 4 steps. And these are the 4 steps over here, okay? And this is the problem we are doing right now. So this is the 4 steps. So again, if I close this, the first step for ODE4 will be again K1, K2, K3, K4, okay? So here you have the basic code for doing the MATLAB part. This is the main file that basically will state the problem, and then we solve it using the fourth method, ODE1, ODE2, ODE2h, and ODE4, okay? And we're gonna compare with the exact solution that was given to us to be equal to -2 cosine t squared plus 3 times cosine t. So now what we can do then is just run this. Alright, so if we run this, just check the time, because so we'll run this, run, change folder. So here we're running for what? Okay, so let's see, here we were running for 10 points between 0 and 1, all right? And here what do you see? So basically the Euler method we know is the less accurate, and you see that the residual is about, this is in percentage, is about 11%. Then the midpoint method, you see this one is already much better. It's the pink one with that symbol over here. Is good at the beginning and then is not that good over here. And then as soon as we move to the Heun's method, that one is really good, and the Runge-Kutta is as well really good. Basically it's just spot on. And here we compare it to the exact. Alright, so this is our first run. So we see over here that this will be an approximation. So now let's see what happened. For example, if we increase, let's say, the number of points. So let's say instead of 10 points we take 20 points. So we should expect what? The time step is divided by 2, so maybe this should go about half, no, for the first order ODE. Let's see what happened. So you see this one basically went to half, and this one was to the order square, so probably order of 4. And you see here the percentage error is very small, or the residual is almost 0, about 0.3 and 5%. So you see now the only one really that stays a little bit off is the first approximation Euler method. Alright, but here you need to be careful. Don't be fooled thinking that this is now accurate all the time, because what happens if we actually look at the rest of all the behavior of this function in a longer period of time. So let's do that. So let's say we keep 20, but let's say we go back to 10 for comparison purposes, but we go to t equals to 3. All right, or maybe more. Let's see how that looks. So this is a trigonometric function, so it will be about 2 pi. So let's say, oops, this is 1. T final, let's say, would be equals to, I mean, it really doesn't matter which value we put, 2 times pi, but, and see what happens. Oh, that's not too good. Okay, so maybe let's go a little bit less, because this one is diverging, which makes this function here to look good. So let's do first 0 to 3, and then we can see what happened. Okay. Okay, so that looks a little bit better. So 0 to 3. So before we were 0 to 1, and these were the approximation. Okay. Now let's see what happened. 0. As soon as we move here, the blue one is exact. The Euler is not good, but not even the Runge-Kutta is good, which is supposed to be the best one. Then is the Heun's method and the midpoint. So basically what happened is that the approximation, I have a hard time to keep up with the change in the function, as you can see over here. All right, so this function over here. So what are the options we have? So you need to select a smaller time step, which means to select more points, and let's see what happens. So let's say now instead of 10 points we go to 20 points. So should that improve a little bit the solution? Alright, again, this one is diverging now. So the other ones are better, but you see actually the one that should be the better is diverging because it's not able to catch up with some of the variation. So let's put over here maybe 50 points. Let's move much higher. I hope now the Runge-Kutta is able to catch up within the changes, and it's not divergent. So you see now, finally, the Runge-Kutta was able to catch up, and is probably the best one compared to there, but it's still not right over the exact solution. So the point over here is that doesn't mean that because here is accurate, that's going to be on the rest of the solution. And if you did not have here the exact solution, how will you know how good this approximation is? Okay, so that's why in real life you need to do convergence test of the solutions. You need to keep making the time step as small as possible until you see that there is no variation on the response anymore, or very small, up to a certain tolerance that you accept. So let's say we're going to put here, let's go large right away. Let's say 100 and run it. Okay, and let's see what happens over here. So still we see that this one now is worse than the other one, so this is still not a very good solution. Let's see what would happen with 500. Obviously, as you increase the number of points, the solution is going to take longer and longer. Alright, so tools, zoom in, let's see what happens over here. Alright, so over here you see that still there is not like one solution that is very, very good, but all of them are kind of going close to it. Alright, so let me do an extreme change over here and put literally like 1000, run, and again let us just go and zoom in. Alright, so you see now they are a lot closer over here, but now really the best solution is the Heun's method, not the midpoint method, and actually here strangely is the Euler method, the one that is the best in this region, but it's not going to be on the other one. So be careful with that, because in one region one method might be better than the other one, but you need to look at the overall behavior. So basically here look at the residual. So you see the residual for the Euler's method is the smallest one in this case, and actually the Runge-Kutta ODE4 might be the highest one. So be careful, because again, not always this one's going to be the best. The most commonly used are this one here in real life, and the last one, to tell the truth. Okay, but I'm curious over here. Let's say right away what happened if we go literally to 10,000. So this is still the best one, and now this one completely diverges, and this one, the ODE2, which was the best one before. So you see this one is literally, for this order, would be this one will be the best. Let me move the time step here now to t final equal to 6. Let's see what will happen. Alright, so let's see. Oops. Looks like the exact is over there. So here the midpoint is horrible. The Runge-Kutta only able to catch up to this point, and it looks like the best one is going to be the Heun's method in order to catch up with these changes over here. Okay, so again the conclusion is that you need to be careful. It's not because the solution is accurate here that it's going to be accurate throughout the whole interval. So you need to make sure to check the validity of your numerical solution throughout the whole interval. Okay, so you see up to here all the solutions were good, basically up to this point over here. Alright, so let me close this, and I'm giving you in Canvas all these MATLAB files so you can play with them, as well as this one. I think if you want, you might have to add this text over here that is not on the files that are uploaded, but anyway, these are just comments and should not affect at all the way the program is running. Let's put here a very small time step. I'm doing that because I'm surprised that the Runge-Kutta 4, okay, is not really following the exact solution. So you see over here that once you go to that very small time step, now all the solutions kind of follow the exact solution. All right, let's see if we can zoom a little bit more. So now again, all right, and still the Heun's method here looks like it's the best, but all the solutions are pretty close if you take a small enough time step. Okay. All right, so with this I will finish this video over here. So let's see, how can I do that? Gonna move this up. So